Math 287, Cuesta College, I'm Joe Vasta. We are doing 1.7 mixing problems. Before we get into this mixing problem, let's go ahead and, it looks pretty innocent. You're mixing some salty water, so why would there be differential equations? Let's take a look at what we have. We'll do a derivation. So we've got this tank full of salty water or brine, and it's being well stirred. You've got concentration of the brine going into the tank, and you have the rate in which the brine goes into the tank. And then you have concentration out and rate out. So you've got this situation, and it doesn't even look like differential equations are involved, but we will see one by the end of this derivation. V of t is going to be the amount of brine in the tank, and that's going to be measured in liters. Okay, V reminds you of volume. A of t is the amount of salt in the tank, and that's measured in grams. Now, concentration in and concentration out, that's your salt concentration. It's going to be grams per liter. R in and R out, so those are rates. Those are going to be measured in liters per minute. So we have all these variables. We actually have 7 things to look at, which is R in, R out, C in, C out, A, V, and T. And some of them are constants in these problems we're going to do, and some of them are going to be variables. So the ones that are constants would be the concentration going in, the rate going in, and the rate coming out. Now, in the real world, those might not be constants, and then, of course, the differential equation would be more complicated. Our variables happen to be the amount of salt in the tank, the amount of brine in the tank, that's the volume, time, that's going to change, and C out, concentration coming out, will change. So the concentration of this brine coming out of the tank is really going to be the amount of salt divided by the amount of brine in the tank. So A of t over V of t, and it will be dependent on time. And A of t is measured in grams, and V of t measured in liters. So you can see that sorry, did I say that right? Yeah, A of t is grams, V of t is liters. So this happens to be grams per liter. Now, dA dt, that's the change of the amount of salt with respect to time. That's going to be Cn Rn minus C out R out. And those units, you can actually do the units on the Cn, which is grams per liter. It's multiplied by Rn, which is liters per minute. The liters cancel, and you end up getting grams per minute. And that's what we have. A is grams and T is minutes. And so this is the change of the amount of salt with respect to time. And we can replace the C out with A over V, and we end up getting this differential equation that we're going to be using when we do the problems in this section. So now we'll go back to the paper. A tank initially contains 25 liters of water. We could, if we want, draw the tank. So it's got some water in it, and in which there is 175 grams of salt dissolved.
A solution containing 3 grams per liter of salt is pumped into the container at a rate of 5 liters per minute. So basically what we have here is some stuff going in. A solution containing 3 grams per liter. So that sounds like a concentration. It's going in. It's 3 grams per liter. Is being pumped into the container at a rate, so here's a rate, 5 liters per minute. So Rn is 5 liters per minute. And the well-stirred mixture runs out at a rate, so there's like a pipe coming out here. So the rates are out of 3 liters per minute. So, do you need to draw a picture when you do your problems? No, you don't. But for the visual people, you might like this. How much salt is in the tank after t minutes? Basically, what they want us to find, our goal, is to find A of t. And I believe what we have is, let's move this a little. We have that formula that we wrote out, which I'm going to say A prime. I'm writing it differently than we saw on that little sheet that was typed up, equals Cn Rn minus R out A over V. Now I know that A and V and A prime, they're functions of t, but I'm going to write it like this because it's simpler on my eyes. So what we're going to do is we're also going to look at some numbers that are not those numbers. We have initially, so there's a keyword right there, a tank initially contains 25 liters of water. So what we have there, those are our initial conditions. At the very beginning, when the clock starts at 0, the volume is 25 liters, in which there is 175 grams of salt dissolved. So the amount of salt at 0 is 175. Let's go ahead and write out this differential equation with the constants. A prime equals Cn happens to be 3, Rn is 5, R out is 3. So my equation says A prime equals 15 minus 3A over V. And so we have that there. Everything's a function of t. And the problem is, in this differential equation, we also have a v, which is a bad thing to have, because now we have more variables than we want. So what I'm going to do, and you'll do this in all your problems, is we have to come up with an equation for v. So I'm going to do that off to the side over here. Now, I don't know what v is, because it is changing, but I do know the rate of change of the volume, dv dt. So let's think about this. We're looking at the rate going in and the rate coming out. What is happening here? Is the tank filling up, or is it getting less? Well, more is going in than is coming out in terms of the rate. So the change, since these are constants, is actually going to be on the positive side. It's going to be 2. So over here on the side, I have dv dt equals 2. It's a little differential equation, and I'm going to go ahead and integrate both sides. The integral of dv dt with respect to t is v, and the integral of 2 with respect to t is 2t, and then we have to put our plus c. Now, to find the c, we use this initial condition. This initial condition says t is 0 when v is 25. So let's go ahead and do that. And some of you feel comfortable with this, but I'm writing this all out for the people who haven't seen these that much. So this is 0 plus c. So it looks like our value of c here is 25, which means now we know that the volume is 2t plus 25. And so that is what we're going to put right here. And things will look a little better when we do. So I have A prime equals 15 minus 3a all over 2t plus 25. So there is my differential equation. Playing the role of y is a, and playing the role of x is t. Let's continue. We have to solve this differential equation. We're solving for a. So hopefully I said a is taking the place of y and t is taking the place of x. This differential equation, I mean, this says dA dt. dA dt on the left side, this differential equation, because of this 15, cannot be separated. It's not separable. You cannot separate the right-hand side as a function of a times a function of t. So we now have to use our other method. This right here is a linear differential equation. So we're going to shift things over here. So I'm going to go ahead and write this as a prime. I'm going to move this to the right-hand side, to the left-hand side, plus we have 3 over 2t plus 25. This is a equals 15. Now, the reason for doing that here is I actually have a linear differential equation, first order, and I'm going to identify this as function p, and this guy right here is function f. P and f are continuous, not for all real numbers. This right here, time would be a negative. That would make it 0. So I'm going to say it's continuous from 0 to infinity, because that's all really we're concerned about. This is an experiment that starts at time 0, and I should have maybe put a bracket there, but I don't think it matters. So the next thing we're going to do is we are doing the method of the integrating factor. The method of the integrating factor says I'm going to compute I of t. Now we're used to saying I of x. This is going to be e raised to the integral 3 over 2t plus 25 dt. Okay, so I'm going to go ahead and use the eyeball method on this. This is e. I look at the bottom here, and the derivative of the bottom happens to be 2. I'd like a 2 on the top, so I'll put the 2 on the top, and I'll put a 1/2 out front. I'll also pull that 3 out front. So now I have e raised to the 3/2, and then now it's time to integrate. The 2 dt is going to disappear. If you don't feel comfortable with this technique of integration, the eyeball method, go ahead and do u substitution. U equals 2t plus 25. And so I'm going to say 3/2. This gives me the ln of the absolute value of 2t plus 25. So we have e raised to the 3/2 ln. Since t starts at 0, this is always going to be positive. I can get rid of those absolute values, ln of 2t plus 25. Now I can't use the popping property of logs, where it's e to the ln and those disappear, until I get rid of this 3/2. And I don't really get rid of it. It's going to be a power up here, because this is the power rule for logarithms. So now I have e raised to the ln 2t plus 25 raised to the 3/2 power. Now, one of the funnest properties of logarithms, this is so fun, that pops, and we have our integrating factor is 2t plus 25 raised to the 3/2 power. So there it is. That is not the end of the problem, but that's a good place to see if things are blurry on the camera. We're doing good. We're at the 15-minute mark. Life is good. Kind of, I guess. Maybe, I don't know. The shelter in place, you know, it gets a little old. Oh wait, we got to show the differential equation. Okay, so what am I going to do? Let's just kind of recap what's happening here. We have this differential equation, which is a prime plus 3 over 2t plus 25. This equals 15. I'm going to multiply this differential equation by the integrating factor. So this is 2t plus 25 raised to the 3/2 power. So this is the integrating factor times a prime plus this, when you multiply this together, you're going to get 2t plus 25 to the 1/2 power times a equals 15. We have 2t plus 25 to the 3/2 power. And this became the 1/2 power because you have one of those down there, and it canceled out a little. Okay, so here's the deal. The left-hand side will always become d dt of y times the integrating factor, but we don't have a y here, we have a times the integrating factor. That will always happen if you compute your integrating factor correctly. Now, you could do a sanity check and say, okay, let's just check this. This is the derivative of a product. The derivative of the first times the second, plus the first times the derivative of the second. Well, the derivative of the second is a little chain rule where you put that in front, 3/2. So you don't see the half there, and then 2t plus 25 to the 1/2. And then the derivative of the inside, which is 2. So the 2's cancel. You do get this. So some people, when they get to this step, on the left-hand side, the first thing they write is this, because they know that will always happen. Okay, so we have 15 2t plus 25 to the 3/2 power. I'm going to integrate both sides with respect to t. And I have the antiderivative gun and the derivative gun all lined up together, so we're just going to get this result right here, a times the integrating factor. I'm going to put my c on the right-hand side with the other c. And over here, I'm going to eyeball this. If you want to do a u substitution, let u equal 2t plus 25. And at any time, you could pause the video and see if you can get the answer for the a of t. That's what we're looking for. We're looking for that right there. Okay. So I want the derivative of this, 2t plus 25, I want that right out front. I don't have it. I have a 15, so you know what I'm going to do? I'm going to move the 15 there, and I want a 2. So I'll just put the 2 right here and put a 1/2 there. That thing's going to disappear because I'm doing the reverse chain rule. So let's go ahead and write this down. This will be 15/2, that's that constant, times. I'm doing the integral of 2t plus 25 to the 3/2 power, or something to the 3/2 power is going to be something to the 5/2 power divided by 5/2, or we can go multiplied by 2/5. Do not forget your plus c. Okay, look what happens here. This guy right here becomes 3. What I want to do is I want to divide by this integrating factor. I end up getting A equals 3. So we have a 3/2 power and then a 5/2 power on the top. This is on the bottom, so this is going to be 2t plus 25. And then we're going to have plus c, and make sure we have this right here, c over 2t plus 25 to the 3/2 power. I'm actually looking for, oh yeah, I've been putting things off to the side. I'm just getting ready for the next piece of paper. Now we might say, hey, we found the answer for the amount of salt, but look what we have in it. We have a C. We don't like that C. So what we're going to do, come back in time with me. We're going to look at this. A of 0 equals 175. I'm going to write that down right here. A of 0 equals 175. That means when time is 0, the amount is 175. So let's put this into our differential equation. This is the general form. It has a C there, and a general solution. I have 175 equals, okay, I'm putting t equals 0 in, so I have 25 times 3, that's 75, plus c over, what do I have here? I have 25 to the 3/2 power, so square root of 20 is 5, 5 cubed is 125. So I have, I'll subtract the 75, I have 100 equals c over 125, and so c is going to equal 12,500. So now I have my final answer. I'll put it right here. I have a little room for this. The amount of salt in the tank after t minutes is, so I'm just copying this down and I'm putting the c in there. 3, 2t plus 25. I could distribute that 3 if you want. But I'll never know because this is a video, so if you want to do that, too bad. 12,500, that's where the C is. This is all over 2t plus 25 to the 3/2 power. There is the answer to the question. Find, or no, it actually says how much salt is in the tank after t minutes. Now, in your homework, they're going to give you some other kinds of questions. Let's go over that, and we'll pretty much be done with this section after we do that. Okay, so I'm going to go ahead and put the next slide on. The next slide, I have the result that I got. A of t equals that. Okay, so that was the answer. And what they're asking is the initial concentration. So how do we find the initial concentration? What we're going to do is, I mean, you could say, well, initially there was 25 liters of water in the tank and 170 grams of salt. Okay, so this is water, or we could put brine, and then this is salt is in there. So what the initial, that's the beginning concentration is you are going to take the 175, which happens to be the amount at time 0, and put it over the volume at time 0. So the amount at time 0, we said is 175 grams and 25 liters. So, I mean, 25 goes into 175, I think 7 times. So the initial concentration is 7 grams per liter. This problem could have been done without doing that differential equation, because these were our initial values. You could actually go to the equations that I computed. Look, I have V. I should actually put this up here. Remember when we computed this and I circled it in orange? I'll go circle this in orange again. You could actually see that, you know, you put 0 in here, you have the 25, and you put 0 in here, you end up getting the 175. You could verify that. Okay, how much salt is in, so the concentration, the concentration is always going to be the amount over the volume. How much salt is in the tank after 10 minutes? Well, this tells you the amount of salt after 10 minutes. We're going to go A of 10, and I would strongly encourage you to use your calculator on this. You're putting 10 into this function right here. And so what I'm getting approximately 176.4 grams, and I went ahead and did the calculation before, so you wouldn't see me just sitting here for 5 minutes pressing buttons. Now, problem 3 says, what is the concentration after 10 minutes? So, look, this is the amount after 10 minutes and the concentration. So, this is the same thing that we did up here. We're going to go A of 10 divided by V of 10. And when we do that, A of 10 is this right here. We computed that in the last problem. And V of 10 is going to be 20 plus 25, so 45. So you're going to take this and divide it by 45. What I ended up getting is 3.92 grams per liter. So this tells us a lot. The concentration is great because it tells me if it's getting more or less salty, and it looks like, you know, at time 0 it was 7 grams per liter, and now after 10 minutes it's 3.92 grams per liter. So it's getting less salty. This is making me very thirsty. Okay, so that's almost good enough to drink, or is it? I don't know. Now here's the interesting part right here. The tank only holds 75 liters. We were never told that until now. How much salt is in the tank just before it overflows? Okay, and then it will ask, what is the concentration at overflow? So I guess the thing is, you know, this scares us, overflow. You know, what? So we're scared about that because maybe you're not thinking about salt in a mixing tank, but you're thinking about your toilet tank and that, or your toilet. You don't want it to overflow. So this frightens us. But the question we'd like to know is when? When is it going to overflow? And if we know the time, then we can figure out how much salt is in the tank. So the overflow is going to have to do with this volume one that I had written in orange. I'm going to go ahead and circle it in orange here, and it says that the tank only holds 75 liters. So I'm going to plug 75 right there for the volume and find out which time that this thing, where it will actually equal 75, where the volume will equal 75. So look what I have here. I have 50 equals 2t, and t equals 25. So it looks like in 25 minutes, time to get out of there because it's going to overflow. And if we're dealing with sulfuric acid or something like that, it's really time to get, or urine or whatever. Okay, baby. I should delete that, but oh well. I mean, I'm not editing my videos, or I actually won't be able to produce that many. So that's not the answer. It says how much salt is in the tank just before it overflows. We're going to go A of 25, and we're going to put that in our calculator, and we're going to round it. And so look, 244.8 0.245. Now on the test, I will tell you which decimal place to round it. It must be annoying some of you. Here's 1 decimal place, 2 decimal places, 3 decimal places. You know, I'm just doing whatever, willy-nilly. But look at this. We can say that, you know, at 25 minutes, there's a lot more salt in the tank. It's 244 grams of salt, whereas at 10 minutes, it's less. So you might get the wrong idea just from the amount of salt. Wow, this thing is getting saltier, and this is why we ask the concentration. So what is the concentration at overflow? We expect that it's actually getting less. So how do I find the concentration at overflow? I go A of 25, which I have in my calculator, it's this right here, over V of 25. And V of 25, I'm just putting 25 in there. And so when I did this, this gave me a concentration of 3.26 grams per liter. Now, look at our concentrations. So I'll circle it in green. Look at this. So we're done with the problem, by the way. We have 7, and then after 10 minutes, the concentration is 3.92, and after 25 minutes, it is 3.26. There seems to be a limit, and maybe some of you can guess what the limit is. And some of you are like, well, let's take out and let's do some calculus stuff. And we can. But the limit of the concentration, suppose the tank can hold as much as you want, infinite amount of brine. Well, the limit then would end up being 3 grams per liter. And one way to do this without a whole bunch of calculus and limit stuff is to take a look at your tank. And what's the concentration going into your tank? It's 3 grams per liter. And for a long time, if this happens a long time, the concentration in the tank is going to start matching the concentration going in. And so that is why it would end up being 3. So here we are doing these problems, and we could say, okay, so why are we doing differential equations? Because you have to check it off your list for being an engineer or a math major. But how does this work in the real world? Well, there have been issues where people they were studying the contaminants in a lake or a pond next to some building or factory, and they would use differential equations to figure out how much contaminant is in the water after so many days or years. Maybe there was an oil spill. And so differential equations, what we're doing here, can be used for those problems. But you want a more concrete example? Let's go to one of the local hospitals. So a student a few semesters ago sent me this picture. He worked in the local hospital, and it looks like a hemodialysis clinic that he works in, and there's a mixing tank. So, you know, sometimes you're just sitting there in class going, wow, who cares about mixing brine? It's the last thing on a lot of people's minds. But look at this. Salt or other stuff is in this tank. Okay, and there's a concentration. And there's the differential equation that we did, and some is coming out the tank. And the correct calculations, you know, like what we've been doing, can mean life or death for 16 patients at a time. So what we're doing, I mean, you might say, oh, I don't want to work in a hospital. But these things, these differential equations will pop up in the weirdest places. You know, you think, it's a tank. What does that have to do with math? Well, you just saw. So this concludes 1.7. Mixing problems. There's only a few in your homework, I think like 6 or so. Be tough. Stay up on the homework. Don't get behind. And I will see you with when I do 1.8.